Good day, everyone. So for this lecture video, I'm going to discuss the answers to Math 2 chemistry. So let's begin. Number one, the density of water is 1 gram per cm cube. Which of the following substance will float on water? Letter A, we have density of gold is equal to 19.3 grams per cm cube. Letter B, density of silver is 10.5 grams per cm cube. Letter C, density of milk is 1.03 grams per cm cube. And lastly, we have letter D, density of ice, which is 0.92 grams per cm cube. Now, this question is very simple. It's actually, you can actually answer this by relating these substances in real life, right? Like, for example, we have water, right? And then if we look at the substance involved, we know that one of the substances would actually float in water based on experience, right? Which is ice. So if you put ice on water, we know that ice will float. So we could easily answer letter D without actually looking at the density. Now, say for example, you encounter a similar question during your Nmat exam, and the substances are not familiar. So, of course, if you're given the density, then you can compare. Now, this is the symbol for density. If um, if we're going to compare, like for right now, we're comparing the density of different substances with water. So say, for example, the density of the substance in question is greater than that of the density of water, which is in this case 1 gram per cm cube. Then that substance is expected to sink. We could think of it that that particular substance is heavier than water. On the other hand, if the substance in question, the density of the substance in question is less than that of water or less than 1 gram per cm cube, then that substance is expected to float. So we could also think of it that as that substance is lighter compared to water, which is actually which still applies to this question. So we could see that the density of ice is in fact lower than that of the density of water. So among all the substances in the option, only ice or the density of ice is lower than that of the density of water. So in summary, the the reason why we answer that it is that the density of the substance, in this case ice, is lower than that of the density of water. In this case, the ice will float on water. Okay, next question. Which of the following is the Lewis acid that acts as reactant in the equation above? So letter A, we have cobalt 3 plus. Letter B, water. Letter C, NH3. And letter D, hexa cobalt 3 plus. So first, we should define what do we mean by Lewis acid. So remember, for acids and bases, we have several theories or common theories. So we have the Arrhenius, we have the Bronsted-Lowry, and then we have the Lewis definition. So Lewis acid is defined as the these are substances that accepts electron in an acid-base reaction. In contrast, when we say Lewis base, these are substances that donates. On the other hand, they donate electrons. Okay. Now, of course, when we talk about Lewis base, because they can donate electron, it's either they have an excess lone pair or uh, and or they have a negative charge. So since electrons are negatively charged, for Lewis acid, most of them are electron deficit. So they lack electron. And in some cases, this lack of electron um, is they are more obvious if the species is positively charged. So we could say that, well, they're either positively charged or partially positively charged. So in this case, we have two options which are positively charged. So we have the actual ion, cobalt 3 plus, and the hexaamine cobalt. So, but in this case, we're going to answer letter A because in this is what we call complexes. And in complexes, it's actually the metal ion that acts as the Lewis acid. So in general, the entire positively charge for this complex is actually coming from the cobalt 3 plus. So we call water as the ligand here. And ligands are generally considered as Lewis bases. And they basically attach themselves by donating their excess lone pair to the Lewis acid, in which case, in this particular question, is the metal ion, cobalt 3 plus. So in summary, Lewis acid, most likely they are positively charged. Lewis base, most likely negative charge, or they have excess lone pair. In this case, ammonia has, though it's neutral, the nitrogen in ammonia contains lone pair, so they can act as Lewis base. Water, the oxygen also has lone pair, so they can also act as Lewis base. Cobalt is electron deficit, it's positively charged, so it's obviously going to be our best option when it comes to determining which one would act as the Lewis acid. Number 3, next question. Hikers light a campfire at night to keep themselves warm. So lighting the campfire is an letter A, exothermic reaction, which absorbs heat. Letter B, exothermic reaction, which releases heat. Letter C, endothermic reaction, which absorbs heat. And letter D, endothermic reaction, which releases heat. So uh, we could actually remove two options. There are actually options here that are, well, by definition is strong. Like for example, letter A, because when we talk about exothermic reaction, these are substances that, or these are reactions rather that releases heat. So you cannot say that, or technically letter A is wrong by definition because it states that exothermic reaction which absorbs heat. And at the same time, of course, when we talk about endothermic reactions, these are reactions which absorbs heat. Now, basically, it's the exact opposite of exothermic reaction. So with that, we could actually remove letter D from our option. But when lighting a campfire, what exactly is going on? So the production of fire, basically when you burn wood to produce campfire, that particular reaction actually releases it. So the answer would be letter B. So lighting the campfire is an exothermic reaction which releases it. So that's why basically we're part of the surroundings. So the system, which is the burning of the campfire, releases heat. That heat is released to the surrounding and it increases the temperature of the surrounding. So we, or probably the hikers as part of the surrounding, would feel that increase in temperature, which would make them feel warm eventually. Okay? Next question, number 4. The molecular formula for caffeine is C8H10N4O2. So what is the empirical formula for caffeine? So this question actually contains irrelevant information, like the atomic number was actually given, but we don't need that information. So when we talk about um, empirical formula, it's actually the uh, largest it's actually the uh, it's the simplest whole number ratio for the number of atom for each element. So how do we get the empirical formula? So we get the greatest common denominator of the subscripts. So in this case, 8, 10, 4, and 2. And then divide everything by, so we divide subscript by the greatest common denominator. So the subscript for this, for caffeine, for the formula of caffeine is C8H10N4O2. So so the common denominator would be 2. So just divide everything by 2. So this is divided by 2, divided by 2, divided by 2. So the empirical formula would be C4H5N2O. So the answer would be letter C. So yeah, so basically the empirical formula is the um if we reduce the subscript into lowest term by dividing the subscript with the greatest common denominator, then we're going to get the empirical formula. So by definition, molecular formula is actually the number or the exact number of atom for each element. So in this case, for caffeine, the exact number of carbon would be 8, the exact number of hydrogen would be 10, the exact number of nitrogen would be 4, and the exact number of oxygen would be 2. On the other hand, empirical formula just show the simplest whole number ratio of each atom or of each element. So in this case, it's not the actual number if it's reduced to lowest term. So it just tells us that the ratio of carbon to hydrogen to nitrogen to oxygen is 4 is to 5 is to 2 is to 1. So basically that's the information that empirical formula gives us. Number 5, the question is which of the following represents a chemical change? Letter A, boiling water to form steam. Letter B, heating lead until it melts. Letter C, burning a piece of wood. And letter D, breaking of glass. So when we say chemical change, basically what happens is that there is a chemical reaction. And if there's a chemical reaction, there should be a change in the identity of the substance. So, for example, when you boil water to form steam, it's basically just still water, right? So you have water is just liquid H2O. Steam is just water in the form of gas, but the identity of the compound is still water. And then letter D, heating lead until it melts. So you have solid lead to liquid lead, which basically still doesn't change the identity of the substance. Now, burning a piece of wood, it's actually an exothermic reaction. Well, there's a chemical reaction, right? And the wood, which is composed of various organic compound, is converted to could be carbon soot or carbon dioxide, carbon monoxide, and water as steam. So there's a change in the identity of the um, substances involved. So we could say that letter C is an example of a chemical change. Now, breaking of glass is still glass. but the size and shape is different. So we could not say, we couldn't say that it's a chemical change. So in summary, when you say chemical change, it involves a chemical reaction. The process involves a chemical reaction. And at the same time, there's a change in the identity. So as of course, when you say chemical reaction, it's the conversion of one substance into another, right? On the other hand, the other example in this question are they're actually considered as physical changes. So physical changes, of course, there are several examples, but common example, especially for Nmat, that well, they would give this as an example of physical change would be phase changes. So when you say phase changes, this is the conversion of solid to liquid. This is by melting, and then liquid to solid by freezing, and then liquid to uh, gas, boiling, and then gas to liquid by condensation, and then gas to solid by deposition, solid to gas by sublimation. So the interconversion of phases of a certain substance would be considered as they are phase changes and they are considered as physical changes. So because the identity of the substance does not change. So boiling water to steam is still water. The phase is just different. Heating lead until it melts, so from solid lead to liquid melt, to liquid lead rather, it's still phase change. And other types of physical change would be change in shape and size, among others. So for example, breaking of glass, it's still glass. If you crumple a paper, if you fold a paper, it's still considered paper. So the identity of whatever substances are inside the paper is not changed.